Hello everyone, so in this video we will be discussing number systems. So from our previous lesson we have discussed number systems and the different number systems that we have, the binary, octal, decimal, and hexadecimal. So for now, we will be discussing how to convert another number system to decimal. Previous lesson we have discussed how to convert decimal to other number system. Now, we will be discussing how to convert another number system or other number system to decimal. And in converting other number system to decimal, or in converting binary to decimal, octal to decimal, hexadecimal to decimal, we need to use the sum of weights. So later on, you will know what is sum of weights of, or how this is, what is the process of sum of weights. So now we have here an example, 11000001 in binary. We need to convert that one into decimal. Again, binary is base 2 and decimal is base 10. So again, in converting another number system to decimal, we need to use the sum of weights. So in this case, we are converting from binary to decimal, so we also need to use the sum of weights. But what is sum of weights, or how, or what is the process of solving this one or converting this one using sum of weights? So basically, we will just rewrite this one, 2, 1, 2, 3, 4, 5. And we have 1. So as you can see, I have rewritten this one in a bigger space because I will be multiplying all of this, each of the binary digits here by 2, and increment the power by 1. So you will start here by 0. Always the right side or the right digit will start by 0, and its power or its exponent will increment. So we have 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, and 2 raised to 7. So we need to multiply all of this, each of this, um, by the base, by the original base and its increasing power. However, this we will not follow the conventional way of multiplying. We will multiply this each. So 2 raised to 0 is 1. 1 times 1 is 1, right? 2 raised to 1 is 2 multiplied by 0, that is 0. So basically all the numbers that is multiplied by 0 is still 0, right? So 2 raised to 6, that is equivalent to 64. 64 times 1, that is still 64. Next is 2 raised to 7. And 2 raised to 7 is 128. Multiply that by 1, that is still 128. So, why is it called sum of weights? Because, as you can see, the weight of our original binary here is multiplied by the base. And then we need to add all of this. That is what we call sum of the weights. So, we need to add all of this, add all its weights. So this is now what we call the sum of weights. Now, 128 plus 64 plus 1, that is just equivalent to 193. So meaning to say, this binary now is equivalent to 193 in decimal. Okay, I hope this is clear with all of you. Now let's move on to another example. Now we have here uh, hexadecimal. As you can see, its subscript is 16, so that means this is hexadecimal, and we need to convert that into decimal. So this is still under the other number system, and we need to convert that to decimal. So meaning to say, we will follow the same process, the sum of weights. So we have BEAD or bead here, and we need to convert that into decimal. So the same process that we did earlier. So I will just write it here. And our base is 16. The original base is 16. So that's 16 raised to 0, 16 raised to 1, 16 raised to 2, and 16 raised to 3. Now, we all know that each of these letters are has an equivalent value in decimal. B is equivalent to 11, right? E is equivalent to 14. A is equivalent to 10, and D is equivalent to 13. Now, uh, we need to get the value, we need to get its equivalent value because this is what we need in multiplying later on. So 16 raised to 0, that is still 16, multiplied by 13, that is equivalent to 13. 16 raised to 0, that is 1, multiplied by 13, so that is 13. 16 raised to 1, that is 16, multiplied by 10, that is 160. 16 squared multiplied by 14, that is 3,584. Next, 16 cubed multiplied by 11, that is equivalent to 45,056. Now you need just to add all of the weights here. So that is now equivalent to 48,803 in decimal. So you can write here 48,803 in decimal. So the same process again and again if you will be using other number system to decimal. So you will just have the same process, which is sum of weights. Next example, we have from octal to decimal. So we have 726 or 726, and we need to convert that to decimal. So we have 7, 2, and 6. Multiply that by its original base, which is 8 raised to 0, 8 raised to 1, and 8 raised to 2. 8 raised to 0, that is still 1. 1 times 6, so that is 6. Next, we have 8 raised to 1, that is 8. And raised to 2, I mean multiplied by 2, so that is 16. 8 squared multiplied by 7, that is 448. Now adding all of this, you will get the sum of 470. So meaning to say 726 in octal is equivalent to 470 in decimal. Again, you can recheck if your answer is correct by doing the reverse process, meaning to say converting 470 in decimal and converting that back to its octal. When you get 726, meaning to say you have the correct answer. Okay, so that is how we convert other number system to decimal. Now we will also discuss other conversions. Other conversions, this means from other number system to other number system. As you can see from here, we have hexadecimal to decimal. I mean to binary. So as you can see, this is other number systems. Both of the base are belong to other number system. Now, how can we convert other number system to other number system? So basically, hexadecimals are composed of 4 bits. Each of the digits of the hexadecimal are composed of 4 bits, meaning to say 0000. And each of these corresponds to 1, 2, 4, and 8. Okay? So again, if it's hexadecimal, that should be in 4 bits. So meaning to say, we need to find the equivalent of each of the digits here. We need to find its equivalent binary. So as we know, binary is just 0 and 1. So this is how we represent binary. Now A, 3, F, and 2. Again, A is 10. This is 3. This is 15. And this is 2. Now, in order for us to get 10, in order for us to get the value of 10 from the binary, we need to know which one should be the on. Since binary is just on and off, right? So if you put 1 in 8, so 10 minus 8 is 2. So we still need 2 in order for us to get the value of 10. So meaning to say 4 and 1 are zeros, or they are off. So if you add 8 plus 2, that is 10. So you'll get 1010. Now, to find 3, you need to have 2 and 1. So 2 plus 1, that is 3, meaning to say other numbers here are zeros. So we have 0011. Now for the F, 8, we will be needing the 8. 8 plus 4, that is still 12, so we might use the 4. 12 plus 2, that is 14. Plus 1, that is 15. So meaning to say all the ones in binary are on. Now, what we need is 2. So we already have 2 here, so that's the only on digit here. So other else are off. So we have 0010. Now we can combine this one. We can combine all the digits here. So we have 1010, 10011, 1111, and 0010. So this is already the result of your binary. Okay, so you just have to find again each digits. You need to find the value of the binary of each digits. If it's hexadecimal or if it's base 16, you will use 4 bits of binary. But if it's octal, just like this one, if it's octal and we need to convert that into binary, we will be using 3 bits, meaning to say there's only 3 zeros here. That's 1, 2, and 4. Because if you add 4 plus 2 plus 1, that is 7. And octal is just from 0 to 7, right? So that is the representation in order for us to get the value of the binary. So we have 7, 1, and 2. So 7, if you try to on 4, that is still 4 plus 2, 6 plus 1, 7. So meaning to say 1, 2, 3. These are all on. Now for 1, 1, 2, and only 1 is on. So 0, 0, 1. For 2, we have 0, 1, 0. So we have 0, 1, 0. Now combining this, we have 1, 2, 3, 0, 0, 1, 0, 1, 0. This is now the result or the binary equivalent of 712 in binary. Okay, I hope this is clear. You might not get confused. When it's octal, you should use 3 bits. If it's hexadecimal, you will use 4 bits. Okay? So next example, we have another example here. We have hexadecimal to octal. So what should we do? For this one, if we are converting hexadecimal to octal, we need to um, trans we need to convert this one first into binary, and then that's the time after we convert that to binary, that's the time we can convert that to octal. Okay, there's no shortcut. So again, you need to convert 16 hexadecimal first to binary before you go to octal. So again, in converting this to binary, we have to use 4 bits, right? So we have to use 1, 2, 3, 4. B is 11, A is 10, D is 13. So this is 1, 2, 4, 8. So 11. So we have 1, 8, 10, and 11. So this one is 0. So we have 1, 0, 1, 1. Next is A. So we have 1, 0, 1, 0. 8 plus 2, that is 10. So we have 1, 0, 1, 0. Next is 13. So we have 8 plus 4, 12, plus 1, that is 13. So we have 1, 1, 0, 1. Now, combining this, we have 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1. Now, this is still the binary equivalent of our hexadecimal, but we still don't have the equivalent octal. So, in order for us to convert the binary to octal, since we are converting that into octal, so we need to divide the binary digits into 3. So counting from the left side, we need to count 3 from the left side. So we have 1, 2, 3. So that is, this should be divided by this. 1, 2, 3, divide, then divide, and then divide. So after that, after you divide it by 3, since you are converting that to octal, so you also again need to find the equivalent of this. 101 in octal, that is only here. 101, that is 4 and 1. So meaning to say this is 5. 110, that is 4 and 2. So meaning to say that is 6. 101, that is still 5. 101 is that is still 5. So meaning to say the final result is 5655. So this is now the equivalent octal of the word bad, or the hexadecimal bad. Okay, next example we have from octal. This is the reverse from octal to hexadecimal. So we have here 7521 in octal, and we need to convert that to hexadecimal. So since this is the original octal, we need to use 3 bits. So here we have 1, 2, and 4. So again, we need to find the result or the equivalent binary of this one. 7 is 1, 2, 3. So 4, 2, and 1, that is 7. 5 is equivalent to 4 and 1. So we have 1, 0, 1. And then for 2, we have 0, 1, 0. And for 1, that is 0, 0, 1. So again, putting that in one line, 1, 2, 3, 1, 0, 1, 0, 1, 0, 0, 0, 1. And then dividing that by 4, since 16 again is 4 bits. So we need to divide from the left side. We need to count 4 bits from the left side. So you need to cut that here. 1, 2, 3, 4. You need to cut that here. Afterwards, you have to find the equivalent of this, since again this is hexadecimal, so we need to add another 0. 8 plus 4 plus 2 plus 1, that is equivalent to 15. 15 in hexadecimal, that is F. And then 101, that is 5. And then this one is 1. So this is now the equivalent, or F51 is the equivalent hexadecimal of 7521. So that's it. That is how we convert other number system to other number system, and other number system to decimal. I hope you learned something from this video, and please don't forget to subscribe and like the video, and I'll see you on my next videos. Thank you.